Morning, guys. Morning, 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 morning. How's it going this morning? You ready to get started? Hey, Lucas. Hey, Kara. Hey, Kelsey. We're here, ready to go. I'm going to show you how this normal distribution is used. How we use it in the real worlds. Do some probability with it. And then you can go do the homework. And then after you do your normal distribution homework, then you'll be ready to go to make your video. Hey, Zoe. How is you? How's you going? Morning, Bo. Morning, morning, morning. Y'all do okay with the empirical probability? I decided it must have been easy because I didn't hear from anybody yesterday. Hey, Giselle. How's it going? How's it going? Y'all must have gotten it done. Bopped it right out. Good. Today's we're just building on it. I'm just going to put words to it. So it'll be scenarios like this, but it's basically the same thing as what we did yesterday. So it's adding the words. I know that always makes it a little bit harder. But if we were to do it in the real world, how does it work? Yeah. Yeah, me too. It is. You got it. A little bit of practice. Now that you've had that one, this one will be easy. You got it. You can do it. Okay, so we'll start. So then that normal distribution, a lot of things are just normally distributed. Like for instance, when we do fill up machines that fill up like Dr. Pepper cans, or in this case, bags of potato chips, they advertise that the bag has 12 ounces in it. But does it really, how do I guarantee then? And I don't want to be sued as the company. Somebody comes along and says, hey, my bags don't have 12 ounces in it. You claim it has 12 ounces in it. So when they're filling up, say the bags of potato chips or your Dr. Pepper cans or whatever, they actually overfill it just a little bit so that they can make sure that, that you're actually getting what they advertise. So they aren't sued. So here's an example of that. We got a machine that fills 12-ounce potato chip bags with potato chips. Not all the bags weigh exactly 12 ounces. It's trying to put 12 ounces in there, or maybe a little bit more than that. But they're not exact every time. This one gets one chip more, this one gets one chip less, whatever. The weight of the bags is normally distributed with a mean of 12.4 ounces. So see, they're filling it up a little bit more. On average, it's 12.4 ounces. And a standard deviation of 0.2 ounces. So here I am in the marketing department, and I want to make sure that I can say that we fill up the bags to 12 ounces. Or, I'm in the legal department, and I want to make sure that you're actually filling up the bags to 12 ounces. So I want to know, if you purchase a bag filled by this machine, what's the probability that it weighs less than 12 ounces? What's the probability that one of our customers is going to get a bag that's less than 12 ounces? So we're just taking what we did yesterday. It's normally distributed. It tells us that it has that nice symmetric shape. that our mean, our median, and our mode are about the same. And it tells us that the mean is 12.4 and the standard deviation is 0.2. So I can use all that. Hey, I didn't put my, I'm missing a haiku. Oh, sad face. So it's normally distributed. My mean is 12.4 and my standard deviation is 0.2, 2/10. So 12 and 4/10 ounces is the mean and 2/10 is the standard deviation. So remember that notation, that's all that means. So now I'm going to draw my normal distribution. I just draw it and find out that probability. So just like you did yesterday, I would do the same thing today. I would first draw that normal distribution. So right here in the middle, 12.4. Put on your standard deviations there. So I'm counting up by 2.2. Y'all do it there and see if you can beat me to it. See if you can come up with the probability before I do. What's the probability I get less than 12 ounces? I'm going to draw it out. So there I just counted by 0.2 or 2/10 up and down. So here's my mean. This is one standard deviation above, 2 above, 3 above, 1 below, 2 below. And then my normal curve looks something like this. And I want to know less than 12. So what is the area under the curve here? What is this probability? Less than 12. What'd y'all get? And then how did you get it? That's another question. Because there are lots of different ways to do it. Mr. Simpson and I might do it two totally different ways. Because he and I think completely differently. So he may do it one way and I may do it a completely different way. So I want to know, what is that probability? And then how did you come up with it? What do you think? What you got? Tell me what you see. If you can't come up to the answer, tell me something that you see on there. Get me started at least. Tell me something to get me started. Y'all still there? Anybody still there? Is it just me today? Am I all by my little lonesome? I might be. Okay then, I'll just teach. I'll pretend that y'all are here. But I'll teach. All right, so here are a couple of different ways I see. I notice that I'm out 2 standard deviations. So, if I start thinking about those 2 standard deviations, this is 95% of it. So one way to think of it, I guess they did, is kind of like, I'm really sad about it, but I think they did all go get coffee. It's fine. Leave me here by myself. A little less than 30. All right, cool. Tell me how you know that. So if we know that this is 95%, keep that in mind. This is 95%. So then how can you use that? If this is 1 standard deviation, 2 standard deviations, and that's 95% of the data in here, there's a couple of different ways we can use it. Number one, we know that the whole curve makes up 100%. So maybe what you do is you take your 100% and you subtract off the 95%. so that, oh, there you go, Bo, that's right. So that each side then, or both sides are 5%. But I just want half of that. So I'm going to take half of that 5%, and you're exactly right, it's a 2.5% chance that I get down here. So it's only a 2.5% probability that I'm below that 12. Another way to do it, this is one way to do it, to use your full 100%. But another way to do it is to do that same idea that this is 95%. Recognizing that you're out 2 standard deviations is very, very helpful. Another way to do it, though, is instead of taking the whole 100%, what if we just said, I know that below this is 50%. You know, anywhere below my mean is 50%. Well, then I could take that 50% and just subtract off this piece, which is half of that 95. So that's another way to do it. And it's interesting to me that some people will do it this way and some people will do it that way. So it just kind of depends on what you see. So in this case, it's minus half of that is 47.5. So you know in here is just 47.5%. Either way, I'm going to get that 2.5%. You're right, though. It's definitely less than 30%. So 2.5% of the time, somebody's going to get a bag that's less than 12 ounces. So maybe in the legal department, I can say, you know, it's only a 2.5% chance that they're going to get the bag, and then how many of those people are really going to sue? So I think that we can err on our mean is good enough and our standard deviation is good enough not to get in trouble. So, you know, then if 2.4%, 2.5% are getting less than this, then how many are getting the right amount? You know, how many of my customers then are getting 12 or more? Well, then getting 12 or more is just the complement of this. So take that 100% and subtract off the 2.5%, or you could take your 95% and add on that 2.5%. And so if this side is 2.5%, that means that the rest of it makes up 97.5%. So 97.5% of my customers are getting the right amount. But you notice that my mean is more than what I'm advertising. I have to make my mean more than that to make sure that I get enough in there. All right, let me just ask a couple other probability questions off of this one, since we already have this drawn, and then I'll show you another example. But this is definitely something that's done in like manufacturing. When they say that they're putting a certain amount in their cans or in their bags or whatever, their mean is higher than what they're claiming, because they want to make sure that they are getting, you know, most of their customers are getting what they claim to get. So let me ask you a couple of other problems, just to practice our probabilities. What if I ask you for less than 12.6? What's the probability that I get less than 12.6? See if you can do that one. I need Bo to stay with me. He's not allowed to go anywhere because he's the only one that's answering my questions. Where are the rest of them today? Where'd they go? That's a challenge. So below 12.6. So I'm going to color what I'm looking at. So everything from here on, they got this though. They can do it. 12.6. So remember, so I'm up 1 standard deviation. You know, remember those z-scores that we did before? So this z is equal to 1 because I'm 1 standard deviation away from the mean. And I agree that below this is 50%. So this piece here is 50%. Then if I just knew how much that was, I could just add them together. So use the fact that from here to here, in other words, 1 standard deviation is 68%. So if you know that this from here to here, 68% of my bags are going to be between 12.2 ounces and 12.6 ounces. Yay! So there's a couple other people jumped in. Yay, they got back with their coffee. So half of that 68, you're right, is 34%. So now I've got this 50%, this half down here, you know, from here down is 50%. And then you add that 34%, the half of the 68. So we do 50 plus 34 equals 84. So this equals 84%. The probability is 84%. All right, let me do another one. See if you can do another one. How about if I do the probability from 12 to 12.6? So we'll make it a little more challenging. What if I want to know a bag between 12 and 12.6? So I'm still at 12.6 there, and then to 12. How would I find that part out? Yeah, it's not too bad, Zoe. Once you get it down, it's not too bad. It's just a matter of knowing those different measurements and then how you can use them. Figuring out, okay, how can I use this measurement to help me? Kind of a puzzle that you're putting together. So like in this case, as I'm thinking about it, I go, well, this is 1 standard deviation out, and this one's 2 standard deviations out. So, yeah, we just figured out, we know that from here to here is 34%. Y'all just did that. You just told me that this piece is 34%. So now, if I could just figure out from here to here, then we'd be in good shape. Or you could have done it that way. Another way to do it is what Bo said. I know from here to here is 68%. So we could use this and then go, well, if I just knew this little piece, I could add it on. So whichever way you want to do it. That's the thing. There are different ways to do it. It's not always just one way to do it. There's not always just one right way to do it. So the question is, how could we figure out that little piece? We haven't done that in the past. Let's do it that way. So, you know, think about then, how could I find out this piece right here? Well, it's out 2 standard deviations. So I know from here to here is 95%. So how could I find out just this piece? Like, that's weird. Maybe let's try to figure out both this piece and that piece. If we could get rid of this middle from the 95, then we'd be left with these two. Good. Divide by, well, maybe before we divide by 2 then. Oh, that would work too. It would work, Aunt Kara, in another situation. So hold on to that for a minute. We'll talk about it in a minute. Okay, good. Subtract it. Eve B says subtract this 95 minus that 68, and if we subtract this off, we'll be left with this. So 95 minus 68 gives me, well, 78, 88, not quite 30, so it's going to be 27. So this piece is 27%, but I only want this one. How can I only get that one? What would I have to do then to get that one? Oh, now divide by 2. Yeah. Now take that and divide it by 2. Zoe, we're going to do it your way next. So if I split it in half and I'm only looking at half of it, then it's 13.5. So one way to do it is to take the 95%, subtract off this 68% to get this 13.5%. Now, I'm still not done because I want it from here to here. So I now know that this piece is 13.5%. So I've got 68 plus that 13.5%. So I have 68 plus the 13.5% equals, well, 68, 78, 78, 80, 78, 79, 80, 81.5. But Zoe's like, y'all are going through a lot of work to get there. Because what she saw was, let me do it Zoe's way now. This is one way to do it. Say, okay, I know this is 68. If I just know this piece, then we're good. So I'm going to find that piece by subtracting, dividing by 2. Y'all did a great job of figuring that out. Okay, but this whole time Zoe's been like, wait, why are y'all doing it that way? Don't we just see? It's a way to do it. You can definitely do it that way. It is not wrong. Y'all went on the loop home. And Zoe's like, I don't want to go that way. Instead, I want to go down 3rd Street. I mean, there's no, why are y'all going down the loop? Seems out of the way. So what Zoe said was, look, I know that this piece right here, because this is 68%, this piece right here, we've dealt with that before, is the 34%. And then, like Aunt Kara said earlier, I know that if this is 95%, well, this piece right here is half of that. It's 47.5%. Haven't we cut that in half before? Yeah. So we know this piece and we know that piece. Can't we just add those two together? So here's the 1 standard deviation, half of that 1 standard deviation, and this is half of 2 standard deviations. So that another way to do it is just to add those two together. 47.5 plus 34 equals, hey, it still equals 81.5. So there are 2 different ways to do it. It doesn't mean it's wrong. It's just how does your brain see it? And you may see doing the 1 standard deviation and then figuring this piece out. And somebody else may see the 1 standard deviation and the 2 standard deviations. After a little bit, you get really, really, really good at knowing each little piece. Like you'll just get to know that this little piece is 13.5%. And that means this piece is 13.5%. Because as you work with this more and more, you're going to get really good at it. So We can also start doing this, you know, talking percentiles. Earlier we said that this 12.6 was 84%. The probability I get something here or less is 84%. So a bag that's got 12.6 ounces, we would say is in the 84th percentile. In other words, it's larger than 85% of the population. So you know how when they talk percentiles on your test scores? So that's kind of the idea that they're using there. All right, how do we feel about all that? All right, let me give you another scenario. Here's one where you see actually in the real world, this is what they do. They fill it up a little bit more just to make sure that you're not complaining. People will complain anyway. Doesn't matter. One of my favorites is the IQ test. So it turns out that IQ tests are normally, their scores are normally distributed as well. So if you've ever taken an IQ test and then they show you your, and they show you your scores, they might show you your score on a normal distribution because IQ scores are normally distributed. I took my son, he has dysgraphia, and so we have to have him reevaluated for schools and such. So when we started, we do not. Mr. Simpson's right. We do not endorse IQ tests because, well, they're not a good measure of who's going to be successful and who's not. So, but IQ scores are a normal distribution. So I took my son to get him reevaluated. He has dysgraphia. I think I've talked to y'all about that before. I don't know if I have or not. So, you know, when he was little, he would write his name, and it would be like, this is what it would look like. That was his name when he'd write it when he was in my kindergarten class. He'd write it completely backwards and all bunched up because of his dysgraphia. So we get him tested, and I find out that he has dysgraphia, so then we can start working with him on coping strategies and such. Well, when he came to Temple College and enrolled last year, we had to have him reevaluated so that he could get accommodations at Temple College, you know, more time on his tests and such. And so we took him to have him tested, and they did an IQ test. And it was funny because they showed him a normal distribution for his testing. Like, here's where you are on this normal distribution. So I was able to explain that all to him. So if you ever have an IQ test done, they'll show it to you on a normal distribution. So anyway, and the mean, or the average, the mean score is 100. And the standard deviation is 15. Fun stuff. He also does things that dysgraphia does other things, like instead of saying, he'll say things like, yesterday I need to do my English quiz. I'm like, well, if it needed to be done yesterday, it's too late, kid. When he means tomorrow. Or he'll say, instead of behind, he'll say in front. Or he does weird things where he messes things up. Yeah, what Mr. Simpson said, I agree. So I'm going to show you, though, how IQ test scores have been used to devise policy and such. So I want to know what's the probability. Well, let's draw this normal distribution out first. So what does this normal distribution look like? So we have 115 is our mean and our standard deviation. So let me just draw that out and then we'll ask you some questions. So I've got 100, add 15, I'm a 115, add 15, add 15, go backwards 15, go backwards 15, go backwards 15. So I'm just subtracting each time. So now I'm going to draw my normal curve on here. I need lots of practice at drawing this curve because I'm not any good at it. I don't know why it's so hard for me, but it is. It's like really hard to draw that. It's tough. Okay, so now here's just a couple of easy questions. Let's start with this. What's the probability that if I randomly choose some person to take the IQ test, that their IQ is greater than 100? So, yeah, I know, I can't draw it. It doesn't seem to matter. Had all this practice, I can't quite draw normal distribution. I don't know what's wrong with me. Art's not my thing. I need more practice. I need a teacher. Make this down here. That will help. It's too late now. Too late, I already messed it up. Next time. Good, and care of 50%. So 50% of the population has IQ above 100, 50% of the population then has an IQ below 100. So then, if you start thinking about things like in schools, one of the ways that you are accepted into the GT program is they do things like they give you an IQ test and they say your IQ has to be greater than 130. And if your IQ is greater than 130, then you're accepted into the GT program. So what is the probability that your IQ is greater than 130? What percent of the population then should have an IQ that is greater than 130? Oh, 2 SDs. So here, yeah. So here I'm looking at 130 or above. All right, Mr. Simpson, I'm going to take your advice. Next time I'll drop it down, see if that helps. Helps me draw the thing. It's so hard. It's hard to draw. What do y'all think? What's that probability? And tell me your process. What are you doing to get there? What do you think? 2.5%? Tell me why, Eve. How'd you get there? Tell me why. I like the 2.5%. I think that's good. I think that's right. I think you got it. This is 2.5% of the population should be there at 130 or above. Tell me how you knew that. I'll show you my way. The way I would do it is say it's out 2 standard deviations. So, there's 2 standard deviations out. That means this part in here is 95%. Subtract that from 100, and I got 5% on the ends. Divide that by 2, and I got 2.5%. Oh, that's exactly what Ann and Kara did. Great, perfect, I agree. But another way to do it would be to say, oh, that too. Because my fat tails are just 2.5%, that's why. Yeah, they are. So another way to do it would be to say down here is 50%, everything below the mean is 50%, and then this is 2 standard deviations out, so this is 47.5%. because it's half of that two standard deviations. So this is 97.5%. Subtract that from 100%. And sure enough, you get the 2.5%. Okay, well, if that's 2.5%, then what's the probability, also in schools, they test you for special ed, and if your IQ is less than 70, then you're placed in special ed. So what's the probability then that, or what percent of the population, or what area under the curve has an IQ of less than 70? What part of the population then has that IQ that's less than 70, according to these IQ tests? Yeah, it's that same, you're exactly right. It's just on the other end, it's that other 2.5%, because this is symmetric to that, so it's also 2.5%. So let me tell you how this normal distribution was used for policy in schools. So you know how I feel about testing. I think y'all have already gotten me off on rants before about testing. But back when testing first was implemented in the state of Texas, I was teaching in schools, so I saw what happened. When schools realized, and schools got a grade based upon the test scores that they got. So what they did was they started noticing, hey, Mikey is going to really struggle with this test. He's dysgraphic, and he's going to really struggle with the test. And so we don't want him to feel bad about doing poorly on the test. Plus, we want to make sure our scores look good. So what we're going to do is we're going to put Mikey in special ed. He's going to be qualified as special ed. And if kids were qualified as special ed, then they got to take either a different test, or maybe they got some sort of accommodations on their test, or sometimes they didn't have to take the test at all. So those kids were excluded. Their test scores weren't included in the test scores, in the actual test scores. So, and you can see that not all schools were being nefarious about this. You can see that for a kid like Michael, who's struggling just to be able to hold a pencil, that maybe taking a test is not best for him. At the same time, maybe that does help to inflate their scores as well. So the state comes along and they say, no, 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 we want everybody's scores. You can't do that. And in fact, we know that only 2.5% of your population should be in special ed, because only 2.5% of the population is got an IQ less than 70. So if you have more than 2.5% of your population in special ed, we're going to dock you, and your grade is going to be docked. So then all of a sudden, 97.5% of the kids are now having to take the test, regardless of whether or not they have special situations. In fact, as a kindergarten teacher, all of a sudden I could not have anybody tested until they were in second grade. So like my personal child who had dysgraphia, I couldn't get him tested at the public schools because they didn't want anybody in special ed. They were holding everybody off to not be in special ed, because if they had more than 2.5% of the population in special ed, it would hurt their scores. It would hurt their grade. So in order to get him tested, I had to go off, and luckily I had a little bit of money to do it, get him tested at SMU and get him tested that way, so that I could start figuring out what was going on with the kid. So that policy of, no, you can't have more than 2.5% of your population in special ed came from this. And then it impacted the school setting. Because then all of a sudden, we couldn't have more than 2.5% of your population in special ed. So policy is actually made around things like this. People see the percentages, and maybe there's something to it. Maybe we shouldn't have more than 2.5% of the population in special ed. But at the same time, maybe we shouldn't be giving third graders standardized tests either. So, you know, policy. So there's your normal curve and how it's actually used, or how I've seen it used. Made it hard to get anybody tested at all because of the percentages. Okay, so I think y'all are pretty good about using this empirical rule. You've done that. But what happens when, you know, all of my percentages so far have been beautiful. They've been right at 70, you know, right at the z-score of -2, or right at the z-score of 2. All my numbers have been nice and pretty. Yeah, me too, Priscilla. It is real life. Right now, you should be seeing it more than ever before with this coronavirus. They are talking, I wish I could have snippeted. I wish I could have recorded what I was watching on the news yesterday, because the stats they were throwing out, they were using these words on the newscast. Prevalence, specificity of the test, sensitivity of the test. They were talking about the testing and using those words. I mean, it's right now, it's so important that you understand the statistics and what's happening. So that you'll stay home, not get sick, not make other people sick. Okay, so, okay, what are we talking about? I know. My beautiful numbers are, you know, I always give you these nice numbers, but what if somebody's IQ was at, you know, 77? And I wanted to know what's the probability that your, you know, IQ is above 77 or below 77. That's not a nice, beautiful one where we can use this empirical rule. Instead, we're going to have to come up with another solution for it. Now, what we can do is we can begin to estimate. Like, I know that this is more than 2.5, but it's less than, well, this is 50, and that's 34. So from here up is 84. So from here down is 16. So I know that, you know, the probability I get somebody with an IQ of 77 is somewhere between 2.5 and 16%. We can start doing that. The problem with that, Eve, is that if I take this and divide it in half, let's just look at that. That's a good thought. It's a good thought. But look at this piece and that piece. Are they equal to one another? Is this piece the same as that piece? So I can't divide it by 2 because this piece isn't the same as that piece. I can only divide it by 2 when they are the same. Because this is symmetric, this piece is the same as that piece. On the wings, those are the same. This piece is the same as that piece because that line in the middle, it's symmetric. But this piece, I'm not dividing it right over the mean, so that piece is not the same as that. So I can't just divide it in half. It's a good thought because that's what we've done in the past. But you can see that they're not the same. So what I'm doing, though, is I'm still trying to find the area under the curve. That's there. And we can kind of approximate, we can say it's between 2.5 and 16%, but I can't tell you exactly unless I do that calculus and that integration, which I'm not going to make y'all do that. So back in the day, we had this little chart that we used where somebody went through and did exactly that. They standardized all these scores. So that, you know, in this one, I had a 70 and a 77 and an 85. But in my potato chip one, I had a 12 and a 12.2, and that would have been somewhere in between there, right? So they standardized these places with that z-score. They said, okay, I'm just going to make a standard normal curve where my mean is always at 0, 1 standard deviation above is 1, 2 et cetera, with our z-scores. And we've dealt with z-scores before to see that. Then they were able to do the calculus to find the integration of each of those, that area under the curve, so they could find the probability for each z-score. And when I was in college, we would use this crazy little chart where we would find the probabilities using this chart. And if you ever take another stats class, they may make you use this antique. So I'm going to show it to you, and then I'm going to laugh at them because it's an antique. It's like using a slide rule nowadays. Why would we ever do that? And one day we'll look back at our little TI calculators and laugh at them too. So, here's our z-score. So, like the z-score of 1, when I want to know, and it's only for a certain direction on my curve, the area under the curve from the z-score down. So then we have to do a little bit of math to figure out, well, what if I want it above? Then I'd have to subtract it from 100. Okay, but this is antique because we now have online calculators to help us out. So let me see if I can show you real quickly one of those online calculators. Let's see if I can be technologically advanced. I don't know if I can or not, but we're going to try it. Can you see that? Distribution. Can you see that? I can't tell if you can see it or not. Let me move this over here and see if I can still see your comments, and yet there. So they have these can you see that? How fancy am I? Y'all can actually see my screen? It's kind of cool. So they have these calculators now that you can do that are normal. Hold on, let me get to a normal calculator. You just type in, look, all I'm going to do is type in normal distribution calculator. Click on that, and it's going to give me the normal distribution. So here I can type in whatever my mean is, so say 100, and my standard deviation of 15, and it draws out the normal curve for me. There it is. Bada bing, bada boom. Not too bad, right? I don't know, is it a redundancy? I'm not physically advanced, I'm technologically advanced. Okay, so then I can ask myself, well, what's the probability that I have an IQ above 70? I wanted to know what's the probability of above 70. And down here it tells me, we said it was 97.5%. So using, I don't know where I'm going because you can't see me. Using that calculator, it's a little bit off from our empirical rule, but this is the more exact version. By the way, when you're doing your homework and when you're doing the problems for me, you're using the empirical rule, but this could help you check to make sure that you're there. So anyway, this is a nice calculator. We don't have to use that anymore. And if I wanted to do something in between, like 77, it'll give me that as well. So you can see why I laugh in the face of those people who are using that old chart, because we don't need that old chart anymore. We have these online calculators that will just tell us the probability. So here's my probability that I have an IQ above 77 is 93.7%. Of us will have an IQ above that. We'll give a score anyway of an IQ above that. So that's how that normal distribution calculator works. All right, let me go back to this. I'm just so proud of myself, those little things like that. I can switch back and forth. That's pretty cool. Y'all learned empirical rule this semester, and I've learned to stream this semester. That's what I've learned. All right, so now what I want to show you is just remind you how to get that z-score, just so that we could compare apples and oranges if we wanted to. That's another thing that the z-score does for us, is it does teach us, it does help us to be able to compare apples and oranges. So for instance, what if I wanted to literally compare apples and oranges? And I know that the diameter of an apple, the average mean diameter of an apple is 3.25 inches. And has a standard deviation of 5 inches. Or 0.5, I'm sorry, 0.5 inches. All right, and then the oranges, so the mean of an orange is, I looked it up, it's about 4.5 inches, depending on what kind of apple and orange you get. And the standard deviation is about 1 inch. So, first, what if I want a 4-inch orange? Well, if I were to find the probability of a 4-inch orange, notice on my number line, 3.25, I'm counting by 0.5s, so that's 4.25. Notice the 4-inch, notice that 4 inches in between the 1 standard deviations and the 2 standard deviations. It's in here. So I know that it's above average. How much above average? Well, I could find a z-score for it. And then for my oranges, I'm at 4.5. Here's my apples. I didn't draw the thing, but there's my apples. Here's my oranges. I've got my mean is at 4.5, and I'm going up 5.5, 6.5, and I want to know what about the orange with a 5.6 diameter. So which one of those is bigger compared to others of its kind? Now maybe we can just look on there and tell. They both are above average. They're both more than 1 standard deviation above average. But let's just look to see which one is better compared to others of its kind. So we use that z-score formula. Do you remember that z-score formula? So that z equals, we're just finding this distance. In other words, we're going to take how far away this is from that. How far away is this from that? So we take our value that we have and we subtract our mean. And then, however far that is, we're going to divide it by how many standard deviations it takes, or how wide our standard deviation is. We're just going to divide it by our standard deviation. So I have x is 4 for my apples, and my mean is 3.25, and I'm dividing it by 0.5. So I have 0.75 divided by 0.5. Maybe you don't like the fractions, the decimals, in which case just multiply by 100. Multiply by 100, and you have 50 over 75. which, maybe that makes it a little easier to see. This goes in there one time with 25/50ths left over, or maybe you reduce it, 25 goes in there 3/2, so that's 1.5. So this one is 1.5 standard deviations above average. My apple. What about my orange? Well, my orange, I do the same thing. The z-score, I'm looking at this one, so 5.6. How far away is he from 4.5? And then how many distances, how many of these distances are there? I'm dividing it by that 1. So I get 1.1 divided by 1, or 1.1. So notice that this one is further along, it's further away from the mean than that one. This one's more standard deviations away than that one is. So that's how we use the z-score. So we go, this apple compared to other apples is a better apple than that orange is compared to other oranges. So we really can begin to compare things with that z-score. So anyway, that's how the z-score works. We've used it in the past. I'm just showing you again in case we use it again here. And because most of the time they have you find that z-score just so you can look on the little chart. And T. All right, one more thing I want to show you. And that is, we've done binomials. So I want to show you with this application what happens with our binomials as our probability gets further and further, further away from 0 and further away from 1. So let me show you. Let me show you with this app. Okay. All right. Here's a binomial distribution. And in this case, in this binomial distribution, I have my population is 100, and then the probability that of success is 0.01. So that's what this is showing. It's the population, I'm doing it 100 trials, and my probability for success is 0.01. So remember when we did binomials, we wanted the number of trials, and then we used that probability for success. And before, we didn't really look at what the distribution looked like. We made our own distribution tables with our discrete data. But here it is. Here's an example of that. Here's a picture of it. Man, my brain just kind of quit on me. Okay. So now I'm going to change this probability. I'm going to get it away from 0. Right now it's really, really close to 0, that probability for success. So let me change that probability to like 10%, which would be 0.1. And let's see what happens as I change that probability from 1% happening to 10% happening. Notice that distribution and how it changed. It went from being right skewed to here it is, looking already a little more like a normally distributed distribution. Or what about if I made it a 20% chance? So I'm just changing my probability. There's a 20% chance. Looking even more normal, right? What about if I make it a 30% chance? So if your probability is not close to 0, let's see what happens if I make it a 99% chance, my probability for success. Oh, when I got it a 99% chance, all of a sudden it's not normal anymore. So, but when my probability for success in a binomial is not close to 0 or 1, so like here's 90%. if it's not close to 0 or 1, it begins to be more normally distributed. And so we can begin to use a normal distribution even with our binomials to talk about our binomials. So let me give you an example of that. So let me do an example where I have a binomial that we can use normal distribution to help us with. So here's an example. What if I have some procedure where there's a 40% chance for success and a 60%, well, that would mean a 60% chance of failure. Well, I know that because this is, I've got two outcomes, and the probability here for success is not close to 0 or to 1, that 40%, it's not close to 0 or 1, and I want to know that if I treat 200 patients, what's the probability that more than 211 are successful? All right, something like that, where I've got a binomial, and yet I know from binomial I can use, I could use the binomial formula. I could use the binomial formula to figure it out. But when I start doing this, more than 211, all of a sudden I'm going to have to do the binomial with 211, 212. Wait a minute. That doesn't make sense. If it's 200 patients, how did I get 200 things? That doesn't make any sense. It's 500 patients. Sorry, that wasn't making any sense. 500 patients, 500 patients. That makes more sense maybe. So I'd have to do the binomial with 211, 212, 213, 214, 215, etc., 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 for all the way up to 500. That sounds like a lot. So instead, what I want to do is use my normal to help me figure out what's the probability of more than 211. So here's what I do. The first thing I need to know is my mean. Do you remember how to find the mean of a binomial? How do we find that mean? Yeah, somehow or another they did. 11 of them snuck in. Should have been 500. Should have been 500. So how do I find my mean? Do you remember with a binomial? That's been a while. That's been like 2 whole weeks ago. Do you remember that it was the number of trials times the probability? So in this time, good. Oh, that's just Mr. Simpson. The number of trials is 500 times that probability here is 40%. Or you could say 500 times 40 over 100, because remember, 0.40, you read this as 40 hundredths. 40% is just 40 over 100. These zeros and those zeros go away, so it leaves me with 200. That's where I was getting that 200 from earlier. Then we also, in order to make a normal distribution, not only do we need the mean of it, but we also need the standard deviation of it. So I don't know, that's been a couple of weeks ago. Do you remember how to find the standard deviation of a binomial? Luckily it was nice and easy. It wasn't that big long chart where we had to find the distances and square things. It wasn't that. We just took that mean it was n times p times q. So we already know n times p is 200. Then multiply that times the 60%, or 200 times 60 over 100, and I get 120. The square root of 120 is not perfect, a nice perfect square, but we can approximate, because we know this is really close to 11, right? 121 would be 11. Let's just call that 11. And then we can begin to get our probability. So now, because we know binomial is approximately normal when the percent is not close to 0 or 1, we can draw this normal distribution. Our mean is at 200, and our standard deviation is at 11. So it turns out that we can use normal even for the binomial if our percentages are good. So normal is a really handy and important distribution to learn. So there I counted up by 11s, and here I would count down by 11s, which is a lot harder. 178 down 167. Let's see if I can do what Mr. Simpson said. This is closer down here. Closer down there. Oh, not 1. Sorry. Not at 1. At 2, it's closer down there. And at 3, it's just like the whole thing, basically. Maybe that's better. I don't know. Is that better? Can I do better? Can I do better? And I want to know, well, what's the probability that it's bigger than 211, that I have more than 211 patients successful? What's that probability? So I can begin to see my, my probabilities there. So what is that one? What is the probability of more than 211? Is anybody still with me? I lost them all. Started playing with apps and I lost them. No, they're there. They're going to tell me what that probability is. What's the probability of, oh, there we go. We did it. We did it. So that's one way to do it. Now you just know, right, that this is 13.5 and that's 2.5. So you just add those two together. So that is definitely one way to do it. Say, well, I know that this piece is 13.5 because we figured that out. And we know that that piece is 2.5. So together that makes 16%. I like it. Or another way to do it would be to say, hey, this is 50%. This piece is 34%. So we could do 100 minus the 84%, which also gives us 16%. So many different ways to do it. But you see that with binomial, we can even use the normal distribution if our probability for success is not close to 0 or 1. And, there you go. Okay, cool. That works. And if our mean, because of that, we can find our mean and our standard deviation, and blah, we got normal again. All right, your job is to go do the empirical homework, empirical rule homework. Do the normal distribution homework. Then you have 3 questions that are your assessment. Maybe it's 4, I think it's 3, maybe it's 4, I can't remember. I have more than one class, and so therefore I can't remember what I did. Anyway, I think it's 3. You are going to do those 3 problems and turn them in. And then you're going to make a video teaching us how to do one of those 3 problems that you just did. Now, I'm not going to be willing to help you on those 3 assessment problems if you haven't done your homework. So I've already had people asking me questions about the assessment questions, and my answer always is, send me a picture of your homework and then I'll gladly help. So I don't want to help you if you haven't done the homework. The homework is supposed to help you to practice so then you can be good at the assessment. That's how this has worked all along. So do the homework first and then work on the assessment. Got it? Got it? Got it? Got it? Got it? Good, Priscilla. At least you're there. I know y'all are really washing dishes, doing laundry. You're like, I'm not by the keyboard, but I'm kind of listening to you, Miss Simpson. I get it, I get it. It's a great thing about being at home. All right, so go do your homework. I'll be online today if you need me. And then tomorrow we'll look at the app that you're going to use for the other task. I'll just show you that app and how to play with it. All right, Math Made Simple, Isms of Math. Thanks for watching. See you in a minute, guys. See you in a minute.